Okay, we'll look at some of the homework problems in section 4.2. And this deals with prime and composite numbers, by the way. And in the first problem, you want to determine whether, or tell whether the number 107 is prime. Well, by looking at this, I know 107 is not divisible by 2. It's also not divisible by 3 because the sum of the digits, which is 8, is not divisible by 3. The last two digits is not divisible by 4. It doesn't end in a 5 or a 0, so it's not divisible by 5 or by 10. Also, it's not divisible by 6 or 8 or 11 or by 9. So here, this is considered to be a prime number. So 107 is prime. Okay. All right, now let's look at the next problem. This deals with the prime factorization. Here we want to find the prime factorization of 2,205. Okay, so in this case here, I'm going to move this up here and write down the number 2,205. One way of finding the prime factorization is using the factor tree. And when we start the factor tree, we want to find two numbers that would give us a product of 2,205. Well, in this case here, I see that this number ends in 5, so let's use 5. Okay, and then we want to divide 2,205 by 5. This will give me, let's see, 451. Okay, and then we double check. Because if I do 2205 divided by 5, this will be 441. So 441, not 451, would be the other factor for 2205. So 441 times 5 will give me 2205. Okay, now 5 is a prime number, so I'm going to go ahead and circle that. Now 441, now I see the sum of the digits. 4, 4, and 1 gives me 9, which is divisible by 3. So let's use 3 in this particular situation. Okay, and then I'm going to divide 3 into 441. That's going to go 147. The other factor will be 147. So it'll be 3 times 147. And I know 3 is prime, so I'll go ahead and circle the 3. Now 147, again, this is divisible by 3 because the sum of the digits, the 1, the 4, and the 7, that gives me 12, which is divisible by 3. So we can use 3 as another factor. And then divide 3 into 147. That will go 49 times. Okay. And then I know I can break 49 up into 7 times 7. And 7 is a prime number. So these circled numbers, or the circled digits, represent the prime factorization of 2,205, which is in this case, now 3 is used as a factor twice, so I'll write 3 to the second times 5 times, and no 7 is used as a factor twice, so it'll be 7 to the second. So this represents the prime factorization of 441. 3 squared plus 5 times 7 squared. Okay. All right, now let's look at the next problem. In this case here, we're going to fill in the missing numbers in the given factor tree. Okay, so here we got some missing numbers that we need to fill in. Okay, let's start from the bottom and go upward. because we can find out what 2 times 3 is. That would give us this missing box. Here, 2 times 3, that's going to give us 6. So the 6 will go here. And then to find out what this missing box is, we multiply 6 times 7. That's going to give us 42. So 42 will go up here. And then finally, to find out what this box is, what the number in this missing box, well, missing number in the box, 42 times 2 will be 84. So that 84 goes up here. And that will complete the tree. Because here, 84 breaks down to 2 times 42. Then 42 will break down to 6 times 7. Then we can break the 6 up into 2 times 3. Okay. All right, number 4. What is the greatest prime you must consider to test when whether 1796 is prime? Okay, there is a rule that tells you what prime numbers you can use to test whether any number is prime, and that's this: p is less than or equal to the square root of n. P is the prime number that's going to be less than the square root of the number that you're dealing with. So in this case, we're going to test p, which is less than or equal to the square root of 1796, which means p is going to be less than or equal to, and if we take the square root of 1796, on our calculator, okay, you'll get 42. So you have to use some prime number that is less than 42. Okay, the biggest prime number that's less than 42 will have to be 41. Now 42 is a composite number, so 41, I know, is a prime number, and that's less than 42. So the greatest prime to consider will have to be 41. And that's to determine whether 1796 is a prime number. Okay, so this right here represents the formula that you would use to test whether any number is prime. Okay, here's the next problem. Let's say we had this: 35 to the third times 55 times 4 to the 14th. And you want to choose the correct factorization. Okay, now let's look at what we have. 35 to the third times 55 times 4 to the 14th. Okay, we know 35, 55, and 4 are not prime numbers. So we need to rewrite these as prime numbers here in this case. That 35, that's actually 5 times 7. And I'm putting the exponent of 3 because that 35 was to the third power, so 5 times 7 has to be to the third power. Times 55, I can rewrite that as 5 times 11. And both 5 and 11 are prime numbers. Times, now what's in the parentheses will be to the 14th power. That 4 is going to be 2 times 2. Okay, now I'm going to simplify this. Anything that's raised to a power that's on the outside, every number in the parentheses is raised to the third power in this case. That 5 is raised to the third power, so I'll rewrite that as 5 to the third, times this 7 is raised to the third power, times 5, times 11, times this 2 is to the 14th, and also the 2 is raised to the 14th. Now I'm going to use the rule where if your multiplying powers are the same base, you're going to add the exponents. So in this case here, I'm going to put my bases in numerical order here. Like 2 to the 14 times 2 to the 14. These bases are the same, so I can add the exponents for the 2. So I bring over the base of 2 and add 14 plus 14, which will be 28. So I have 2 to the 28th times, now I got 5 to the 3rd times 5 to the 1st power. Again, I'm multiplying powers of the same base, so I'm going to add those exponents here for 5. So it's 3 plus 1, that's 4. So it'll be 5 to the 4th. And then I'll bring over times 7 to the 3rd times 11. So here, this will be the correct prime factorization of 35 to the 3rd times 55 times 4 to the 14th. Okay, which is in this case 2 to the 28th times 5 to the 4th times 7 cubed times 11. In this case, that's answer C. Okay, and finally, number 6. A patio is to be built with 80 tiles. How many different rectangular arrays can be arranged? In this case, we can come up with, I'm going to do this by coming up with factors of 80. In other words, a pair of factors, a pair of numbers multiplied together that will give me 80. And I start with 1 and 80 because I know 1 goes into each number, that number of times. So 1 goes into 80, 80 times. 2 is another number that I can use. 2 goes into 80, 40 times. Can 3 go into 80 evenly? No. 3 can go into, no, I'm sorry, I just mentioned that. 4 can go into 80, 20 times. What about 5? Can 5 go into 80? In this case, 16 times. 6 can't go into 80 evenly. 7 can't go into 80 evenly, but 8 can. 10 times. 9 cannot go into 80 evenly, but 10 can go into 80 evenly 8 times. But notice I have 8 and 10. So if I have a pair of factors that repeat, that tells me that I have listed all of the factors for that particular number. So these are all the factors of 80. And if you see here, there are 1, 2, 3, 4, 5 different ways that I can arrange the patio. So here, the patio can be arranged in 5 different rectangular arrays. 1 times 80, 2 times 40, 4 times 20, 5 times 16, and 8 times 10. Okay, so this should assist you with some of the homework problems in section 4.2.